Finally, I'm home. I'm home. Sheila, music, hi-fi, volume, comfortable.
I cannot do that now. Someone is
Who
waiting.
is it? My wife?
No, someone else. You are late.
What?
They are waiting. Look at the camera.
Camera.
Yes,
Oh my God. You opened the camera right
yes.
now?
About 5
Hey
minutes
guys,
ago.
it's Ferdinand Dandy here of OFW Profile. Oh no. Hey guys, it's Ferdinand Dandy here of the DIY Travel. Not this channel, not this channel. Hey guys, it's Ferdinand Dandy here of the DR 100 Watt Concept Project. And I'm really sorry guys. I'm really sorry. I'm late. It's like 1:20 in the morning. I just arrived home. It's really crazy this days. Sorry, I should not show this one. Now you know where I'm working. I hope you did not see that. It's really crazy working in the company right now. We got the manufacturing issues, bench tests, design, quality, customers, meetings, project management. It's really crazy. That's my life right now. So I don't have so much time about the video blogging. But anyway, guys, generally, what about you? How's life going on there? I mean, how's our hobby, our DIY hobby? I mean, are you still listening to your DIY build amplifier? Well, I hope you enjoy it. I'm really enjoying it, especially with my own design, the DR 100 Watt Concept Project. And of course, if I'm not in the DR 100 Watt Concept Project, I'm listening with my copycat earbud or with my headset in here. Well, I'm actually want to take this video to update the project on the Class D. Well, no one actually asked for the update, but because I mentioned it in one of my videos, I mentioned actually of sharing whatever my adventures with the TI chipset, like the HD Ultra HD power amplifier Class D from Texas Instrument. That is the TPA3251X series. Which I mentioned about the big brother, which is in here, the middle brother, and the youngest brother, which is the TPA3250. It looks like that no one talk about that. So I removed it from the three brothers. But I added another, I don't know if this is the real one. They mentioned it as a TPA3255, but I'm not really sure about it. But anyhow, this is the idea that I have right now, that I'm still continuing the TPA325X series adventure with the TI Class D power amplifier. I never stop. In fact, I already published my report about the parametric test, or that so-called electrical performance test of the TPA3251, as well as the TPA3255, which is mainly concerned on the maximum power. That is that kind of power that most people would like to know for each of the amplifier. How much power the power amplifier can deliver to the load. And I have done that report already, published in my personal website, including how I'm going to test it in a process by process based on a kind of a standard that they're talking about, like the FTC Title 16 Part 432, which is including the preconditions, which many people fail to do that one. A precondition for 1 hour before you're going to crank the volume to its maximum power. Okay.
Here you go, the moment of truth. It's the electrical performance test of the Ultra HD Class D power amplifier.
It's actually 1:20 in the morning right now, and I'm still alive in here doing a kind of parametric test. I would say this is basically a condition for the FTC Title 16 Part 432. And you know what's that mean? It's from the USA, the USA standard for claiming the output power of an amplifier in a home entertainment. Guys, let me take a break for a moment. I wanted to have my snack. I'm really hungry. At about 1:30 in the morning. Oh, Sheila, would you like to take over?
All right, I can take the explanation in a much straightforward way.
Would you like me to show you in the video?
No, I don't like.
Why not?
I am shy.
You're so attractive, Please help me to explain about I'm having my snack. And gonna change my clothes. It's so hot right now.
All right, have yourself comfortable. Hey guys, are you with me? I will now present the electrical performance test. I will start with the safety bulb. This old school safety precaution is needed mostly in Class AB testing, but it's worth mentioned here in the name of safety. It is also important to take note of the real-world resistance of the resistive load. It's worth to measure it to know the actual value, instead of just assuming a 4 ohms. What Dandy done was, he observed the module from 6 in the early morning before he go to work. He listened to music along with his 2 buddies which were also enjoying listening to the music. When he arrived late at night from one hell of factory visit, he continued the electrical performance test at 12:30 in the morning. Take note of the base temperature in the room. It's about 30 degrees. The emphasis of the test being shown here is the precondition described in the FTC Title 16 Part 432 of the Federal Trade Commission of USA. This specify the use of sine wave as input signal with an output power of 1/3 of its rated power, both channel driven for 1 hour. In short, soak test.
The USA standard for claiming the output power of an amplifier in a home entertainment.
From the 30 degrees inside room temperature, the heatsink surface temperature is now rising to 36 degrees, and clock is ticking toward the 60 minutes. While in this process, he is also monitoring the offset voltage of the left and the right channel through the 2 voltmeters across the 4 ohms resistive load. As the clock is ticking, the heatsink surface temperature dramatically increases towards 71 degrees. This is from 30 to VDC supply at about 25 watt output power per channel at 4 ohms. Resistive load.
Look at that, man. Look at that.
The pure resistance load became hot as well, so Dandy used the electric fan to cool them down.
Reinforcement from the bookshelf speaker in order to put the electric fan level up a little bit as it needs to cool down the resistive load. This is really getting hot right now. Just about 30 minutes and there it goes. While the temperature at the room is just 30 degrees 30.8 degrees centigrade. And guys, I'm testing this one at nearly 1 o'clock in the morning, and if I need to get that into 1 hour, so I need to finish this one at about 2 o'clock in the morning. So what I'm going to do then is to just be alert if there is some kind of burning or whatever it is there. And I'm going to watch some movies from my other computer. This is the computer that doing the data acquisition and as well as the monitoring what's the signal is all about. Let's just take a look at what's the signal actually. Let's do that one. Well, it's almost there. I just need 2 minutes more, and we've got completed the 60 minutes precondition sock test. And the movie is not yet finished. Let's see what's the status of the offset voltage right now. So in the left channel, designated by the L, is a 26.5 millivolt, and in the right channel, there is a minus 10. No, it's not minus 10. It's minus 101.1 millivolt. And the current temperature right now at the heatsink surface is about 80 degrees centigrade. I mean that one, which is the temperature K-type sensor at the surface of the heatsink. So it's been like 1 hour and 7 minutes past, and that's finished the precondition right now, and I'm going to crank the volume right now. Okay, that is 1% right now, 5%. I won't be able to get that 10%. The power supply will going to drop out because I can see that the power supply will shut down itself. I put the switch mode power supply at the side, so you just can monitor the green LED over there, and that is the power actually. So when I'm going to crank this one, power, what is going on right now? Okay, so there is a voltage swing at the left and right is 10 volt RMS, and I just have to monitor the power right now. I'm going to focus that one and monitor this one also. So we're going to crank the power right now. Okay, oh, it's fault already. All right, so there you go. So, and 20, 21, 22 volt, and there you go. Okay, so this one is already off. So it's the power supply that really, you see, it's going to be off. That should be the fault LED actually. And if I'm going to crank the volume right now, and there you go. It died. So I'm going to reduce the volume right now, and there you go. It's just like 1, 2, 3, 4. It's about 4 seconds. Going to increase the volume. It died. 1, 2, 3, 4, 5, 6. It's about 5 seconds. Let's do that again to see the maximum voltage swing at the load before it going to shut down. This is caused by the power supply. Now it's 16, 17 volt the RMS, 19, 20, 21, 22.3, 22.8 at 3.9%, 23. All right, we got the 23, and then it died out. So this is for the right channel, and let's see. We get 15, 16, 17, 18, 19, 22, 23, 23, and then died. So it's basically the same for the left and the right channel. So I can just put it right here. I know that this is the right channel because it's a red color, so I can know about that one. Put that one at about 1 watt of power at the right channel. That's what we can see right now, and that's pretty good actually, 0.02%. So I'm going to do the left and the right channel, and you can see the distortion in here. The left is the yellow one, and the right is the red one. So if I'm going to see the left only, you can see this distortion first noise. And if I'm going to see the right only, and that's the one, and put them together, you can have a nice reading. And I'm going to capture that one, a print screen, and a distortion at 1 watt, so I can see them distortion at 1 watt at 36 volt, and we can capture that data actually, and there you go. So this is the input sensitivity actually. It's 1.1258 volt. That's a volt RMS, and I cannot make use of this one because of the grounding system in here. So I better use the oscilloscope without the power, just only powered by battery right now, and it is a mobile, and there is no grounding connection right now, so that can work. Let me put that into a better perspective to monitor the residual output of the clock frequency. 606 kilohertz, which is this should be the clock frequency of the class D. And if you're going to minimize that one, that's how it looks like for the residual output of the speaker terminal, which is about consider about 220 or 200 let's just say 215 to 225 millivolt RMS for the left and the right channel. And it looks like it's very scary, right? Because you can see all of this stuff right now keep jumping 635, something like that. And there's no way you can hear that one as a normal human being. It's really scary if you take a look at it about this, because you can't see this one in a normal class AB power amplifier. Again, I like to scare you guys. But the more you understand it, the more you understand about the concept of class D and the real world performance, not just like a dream. Try to study it, evaluate it, and after that, the more we evaluate it, the more we test it, the more we understand class D.
Let me make it quick. Dandy also measured the power bandwidth and used 0.5% distortion. Then he find the highest frequency at which at 39 kHz. He then measure the efficiency by comparing the input power against the output power at different power level from 1 watt, 2 watts until the maximum power. The efficiency is the output power of the amplifier divided by the input power multiple by 100. My gosh, it should have been 2 in the morning, yet he's still working on the test, and this time, he is observing the cleanest output signal.
Now you can see a little bit distorted in here already. Now this is fine. This is good, and when you increase that one, I can see the distortion over there, which is the same in here. Just like you got that kind, you can see the cursor in there. Let me emphasize that one. That's the one in there. You can see that one. Oh, sorry, okay, that's a perfect one. But when you increase that one, you can see as a little bit distortion in here. So I can see clearly here the right channel get a distortion, as we can see also in here. And try to increase that one and observe the waveform. And it looks like that the right channel is getting better right now at 11 volt swing, much better right now at the 13 volt RMS swing. And if I'm going to put that one into 50, you can see basically that this signal right now is much better. And let's see what's the distortion right now. Yes, it's indeed so at a 13 volt swing, then we can see that the distortion is much better right now.
He really put an effort to show the artifacts which only happening in Class D amplifier. Even this amplifier is called Ultra HD. Artifact and distortion somewhere in the waveform still exist. It's no exemption, but it was minimum.
So basically this is the test for the 8 ohms load. As you can see, the 4 ohms resistive load has been changed to 8 ohms with that big power resistive load. And the offset voltage is absolutely stable. After several hours, there is minus 20 on the left channel. That's the one. And that is about plus 16.9 millivolt on the right channel, which is quite good. And about 39.4 degrees centigrade at the surface of the heatsink when we just drive for about 1 watt of power, both channel driven at the resistive load.
The test for 8 ohms load is the same as the 4 ohms load, so there is no need to repeat the process in this video.
That ends my electrical performance test for the TPA3251, which is absolutely a nice chipset from Texas Instruments. And thanks to these two batteries in here, the DSO2820E, which is from Virtins, and the other one is the QA401 from Quant Asylum, which provide me a nice screenshot, and it makes my life easier to generate the report. I think I owe you all the setup. Maybe it's going to get me a copyright of it. Let me tell you about the setup, which I wanted to start it with the household power, which is I have a power meter in here where I can monitor the current consumption in AC power, and I can also see the power factor and the power consumed. And this is where I put the switch mode power supply. It's a 36 volts 6 ampere. That power supply is not a standard power supply, but I able to get it from FX Audio power amplifier, the one that I'm using for the D2160. And then the output is 36 volts, so that's the supply, the maximum supply for the TPA3251. That's for the AC and DC. And the source of signal is an external AF generator. I'd like to explain about that because I should have used the internal from the Virtins multi-instrument, but there is a technical problem on that because this is not a floating output, one of which is a grounding, and the other one in here, which is the output, is connected also to the speaker BTL. And when I'm going to connect that one, the ground will basically connected to one of the pins on the BTL speaker output, and that will be connected to ground, and it will going to set the amplifier into its fault mode. So that is the reason why. So I'm going to use an external one, which is grounding isolated, and then it goes to the input 1 kilohertz signal sine wave, and then the output is a BTL, which is very careful in here because in the BTL mode there is basically no plus or minus. Yes, that is correct if you are using a speaker independent, but when you are doing a parametric test like this, wherein the equipment have the ground, and if you interchange that one between the left and the right channel, then it gives you a kind of error reading, not only on the equipment, but also sometimes it triggers the protection of the TPA3251. So be very careful of that for the PTL. So that is also the reason why I cannot make use of the Meguro distortion for reading the distortion and the AC voltage swing at the load, because this one in here, basically there is a ground in here, and that ground is basically we're going to connect to one of the output of the PTL, and it's not working. Especially here in China is that we have a 3-prong plug from the AC. We got the neutral, the live, and the ground, and that makes it more complicated. So that is just important things when you are doing a PTL configuration for the output of an amplifier, and that is something that I experienced actually. So the PTL output of the TPA3251 is where I connect the dummy load, which is a 4 ohms resistive load, and that is a 100 watt resistive load in here. Oh, it's still hot. Oh, it's still hot. Oh, I told you it's hot. And then I need to measure the voltage swing across the resistor, and I'm using the multi-instrument, the DSO2820, left and the right channel. Again, I'm be very careful of which is the ground, because somewhere there is a ground in here. And then in parallel to the output is going into the QA41, the Quant Asylum, for measuring the distortion for both the left and the right channel. And that's totally the setup. And then the monitoring for the multi-instrument, the two-way 20 and the QA401 goes into the PC, and this is where I take the data, screenshot, captures, and so on and so forth, so I can make the report. And finally, something that I can, don't miss it, it's about the temperature. So I have here a DAQ for measuring the temperature at the surface of the heat sink, and that is being data acquisition and also connected to the PC by the USB, and I can able to take the temperature every 5 seconds, and later on in the report I can able to grab the temperature profile during the soak test. That is basically the setup. I think it's completed now, and my voice is a little bit sleepy right now, so I have to go to sleep right now. Down, power down, power down, and, okay, all right, power down, power down.
It's a long video, guys, but do you know the making of this video takes a week to make sure the measurement are correct, generate, report, and make this video presentable. He do the ray testing to see the repeatability and the measurement stability.